Good afternoon again. My name is Michał Jarosz, and I'm an employee of Cybernetics faculty in Military University of Technology. Today I will talk about the formal verifications, verification of security properties for the protocol which I developed. The work was created with in cooperation with my supervisors. The main goal I want to achieve is to build a secure, trusted communication channel between IoT devices in federated environments, that is in environment that consists of different organizations. Each organization may have different security policies and choose different conditions for establishing a connection. The main challenges include the dynamic structure of federated environments, the limitation of IoT devices, their diversity from very weak devices to devices with their own OS. We also need to consider the scale of the whole system. Devices can be 100 or 100,000 or more. The number of devices itself can change over time, and the number of organizations that will make up the federation also can change. To solve this problem, I propose to use a distributed ledger as the main distributed storage for credentials, and reading and writing of data can be accomplished through the use of smart contracts that will meet the organization's policies. In the solution, I use Hyperledger Fabric as a distributed ledger implementation. The purpose of this work is to present the result of security analysis of developed protocol. So now I would like to make a brief introduction to this protocol. You can distinguish three main components in the protocol. The first component is IoT device, which realize its goals and communicates using COA protocol with the application gateway, and the application gateway, which is the second component and is responsible for processing requests from IoT devices and communicating with distributed ledger nodes. The IoT devices doesn't need to know the exact architecture of distributed ledgers, which is dynamic. It only needs to know one application gateway. And application gateway also filtering out of invalid and malicious messages, convert from COA protocol to TLS and vice versa, due to the fact that Hyperledger Fabric requires TLS with certificates, while IoT devices must use lightweight cryptography and lightweight protocols. And the last component is distributed ledger nodes, which are responsible for building, maintaining the distributed ledger. Distributed ledger nodes communicate with each other to vote about adding a new data to the ledger. But if you just want to read data, such mutual communication does not take place because each node has an identical copy of the ledger. Authentication in my protocol is based on the trust that only device and the distributed ledger node can create the encryption key that is used to encrypt the message. This key can be created based on device data, hardware and software, using physical callable function or using generated random data. In the case of first and second, the device doesn't need to store the values because it is able to reconstruct them for itself. However, in the last case, the device must store the generated random values. Of course, the values from which the key will be created must be stored in a distributed ledger. For this purpose, it is necessary to register the device. In addition to registration process, there are two other operations in the protocol. Communication of the IoT device with the ledger node and the communication between IoT devices belonging to the same or to the different organizations. In the article, I with my supervisors described all operations, while during this presentation I will only present the registration operation and the communication between IoT device with the distributed ledger node. In the registration process, the device must send a parameter array that describes the device. The parameter array contains values from one of the three categories presented 2 or 3 slides earlier. The array must send to the distributed ledger in a secure way. This is possible in 2 ways. First, we can connect the device directly to the node, and the second, we use one of the one-time password along with a temporary ID. And the result of this registration process is the writing of the parameter array in the distributed ledger. At the moment, only device and distributed ledger can create a key for this specific IoT device, and the device in this phase also receives an identifier. If a device wants to send some data to distributed ledger, it must generate random values, and these values correspond to the indexes in the parameter array. The device obtains the value of these parameters by executing certain commands. The key is the result of the hash function from the concatenation of hashes of these parameters. The device must generate the nonce value also, and the value and the data along with the current timestamp is encrypted with this created key and this generated nonce. And the message in this form is sent to the distributed ledger via application gateway. The distributed ledger can reconstruct the key. The node can reconstruct the key based on parameters numbers, which are indexes of the parameter array stored in the ledger, and decrypt this message, this encrypted message. The response is prepared in a similar way and sent to the IoT devices. Building a secure communication protocol requires verification of its security properties. Such properties include, for example, authentication of the communicating parties, the confidentiality and integrity of the transmitted data, and the equivalence property, that is an attacker cannot distinguish between any 2 stages of the protocol. And formal verification can confirm or deny that the protocol is secure. A protocol can be mathematically formalized by symbolic and computational model. In symbolic model or Dole-Fiao model, cryptographic primitives are represented as black boxes. Messages are terms in these primitives, and the attacker is restricted to using these primitives. This model makes the execution of automatic proofs relatively easy. The symbolic model is robust to attacks if no attack can occur for each trace. By trace, I mean one run of the protocol. Research progress on this type of model is considered highly advanced. In the second model, the messages are strings of bits. Cryptographic primitives are functions that operate on these strings, and the attacker is any probabilistic Turing machine. This model is generally used by cryptographers. A computational model is robust to attacks if no attacks can be occur for every trace except those with a negligibly small probability. And the computational model is more realistic, but still, since it is only a model, it will not give us an answer to whatever the developed protocol is resilient to some attacks, such as side channel attacks or physical attacks. In the case of computational models, most of the time, cryptographic properties have to be proven manually. The proofs in this model are more difficult to perform and analyze, and this type of modeling is also less mature than symbolic model, and therefore we didn't use this type of modeling. There are many tools that are based on symbolic modeling. For the analysis of our protocol, we have selected a Verifpal and Tamarin prover. Both are widely accepted and are currently used by researchers and practitioners to analyze security protocols. Verifpal supports fast modeling of a protocol and the verification of its basic properties like message secrecy and authentication. On the other hand, Tamarin prover is more powerful tool that can be allowed us to verify a protocol in more detail. Both tools also verify the model automatically. I also think, based on my experience and knowledge, Verifpal and Tamarin have the greatest capabilities in this type of modeling. In the case of modeling with Verifpal, modeling has a very intuitive flow. We simply describe the next steps of the modeled protocol. On the slide, I have presented the main modeling steps. At the beginning, we define what each principal does. In this case, principal device A knows some values like their ID and data which want to send. We can model the process of generating random values, and Verifpal has defined cryptographic primitives such as asymmetric and symmetric cryptography, authenticated encryption, Diffie-Hellman key exchange, digital signature, and secure hash function, which can we use in our model. Verifpal doesn't allow for the creating new additional cryptographic primitives. In the next step, we must to determine what is sent between the principals, and such steps of what principal does and what is sent between principals can be many. Finally, we specify what Verifpal should verify. The approach of modeling in Tamarin prover is quite different from that in Verifpal. For the Tamarin prover, think of protocol as a set of states where information not passed to another state is forgotten. At the beginning, we define what operation we will use, and then we write some rules for transitions between states in the protocol, and the conditions themselves are written as lemmas, which Tamarin prover verifies. An example of the lemma is shown on the right. The purpose of the models developed was to confirm the secrecy of communications, the authentication of parties, and the freshness of transmitted data. For both tools, we had to apply some simplifications. All operations described a few slides earlier were modeled and analyzed. The result of the analysis for each operation was positive. Using these two tools allowed us to confirm that the protocol we developed is secure and provides the required security features. Using two tools reduce the probability that our proposed protocol did not meet our criteria, because both tools use different detection mechanism. In the case of Verifpal, one false positive appeared, which can be ignored. Verifpal thought that in that case it changed two values and it will be able to impersonate as a distributed ledger node. However, in real-world environment, such an operation will not take place because nonce cannot be equal to null. Some conclusions for the end. The fingerprint-based authentication scheme is practically realizable. The proposed protocol can be considered safe. The analysis process is useful for analyzing the security of protocols to identify necessary changes and improvements. And currently used security tools are mature and widely used, but require knowledge in modeling and analyzing the results. Thank you for your attention. Maybe you have any questions.
Thank you for presentation.